Is it audible now? My pin was not properly inserted. Is it audible now? Okay, good.
Yes, sir.
And
Yes.
immediately guys tell me, because I was talking for 2-3 minutes and nothing was happening. Happening in the sense you guys are not able to hear me. I was just talking without the knowledge that you guys are not able to hear me. So hopefully you guys can hear me. I will repeat whatever I did. I was just trying to summarize whatever we did in the first two lectures. Okay, I will repeat that again. In the first lecture, we have gone through what are the screws with the revision of understanding of the screws. What are the power screws? Then we have seen different forms, acme thread, square thread, buttress thread, different forms we have seen, and what is multi and single star thread. We have gone through that, and then quickly we have gone through the terminology. In that we have seen pitch, lead, all the diameters and all that. Okay. Then we started with the understanding of power screws, why we use it, and what are different forms, what are the advantages, disadvantages, and importantly, then we have seen what is the mean diameter of the. In case of square thread, it is outside diameter per inside diameter by 2, right? And importantly, relation of helix angle and lead and mean diameter. Tan alpha is equal to L upon pi dm, where L is lead, dm is mean diameter, and alpha is your helix angle. Okay, we have seen that. And in last lecture, we have seen that what is the torque required for lifting and lowering the load. This is the important concept we have seen, that for to raise a load, we are going against the friction and we are going against the gravity. So obviously the load for raising will be more, and it was we have found out that torque required mt is equal to w into dm by 2 into tan phi plus alpha. Just remember this, mark this equation. Torque required for raising the load is w into mean diameter by 2 into tan phi plus alpha. Okay. Similarly, to lower a load, the same thing equation, but with the sign will be negative. So load or the torque required to lower a load, right, is equal to W into mean diameter by 2 into tan phi minus alpha. So these two important equations we have seen last time. Torque required to raise and lower the load, and we will use these concepts for today's session to know what is what you can say a self-locking screw. Okay, so we'll see that. And also lastly, we have seen for this acme threads, what was the efficiency. Right? So we have seen that. So the torque required for acme threads. Efficiency we will see in the next lecture. Okay. So we'll start with today's session with the understanding of what is self-locking screw. Now, if you see the equation or the torque required to raise or lower the load was, we have seen that, right? It was basically to raise W into dm by 2 into tan phi plus alpha, and to lower the load, it will be W into dm by 2 into tan phi minus alpha. Now, to raise the load, there was a tan phi plus alpha, right? So that means that torque can never be zero, right? But if you see, what you can say closely, this equation of lowering the load, a torque required to lower the load, this equation, what is in on your screen right now. If you see that, you will see that this torque could be zero, means because there is a negative sign. So somehow we are able to manage these terms phi and alpha. We can make this empty as zero. Now just see phi and alpha. So if somehow tan this phi minus alpha is zero, then your torque will be zero. When that is possible, when phi is equal to alpha. So when phi is equal to alpha, that time tan it will be tan zero, and that time torque is zero. That means what is that? Torque required is zero means without giving any effort or without putting any torque in, you will get the output, or you can lower the load. Are you getting my point? So that is one scenario, and other is when phi is less than alpha, right? That time this phi minus alpha will be negative, and tan of negative terms is negative. So your torque required is negative. That means in a case when phi is less than or equal to alpha, that time you will not require any kind of torque to lower the load. What does this mean? This means that to lower this kind of a screw where phi is less than alpha, we will not require any load and it will come down by itself. Okay. Now, what is this? This is a concept called as something, we will use this for the self-locking screw. Now, this property, it will come down without any kind of, what you can say, additional putting load. Still, it will come down, or the torque will be, what you can say, as negative. That means your screw will come down without putting in effort. This concept is called as overhauling of the screw. Okay, this is opposite of self-locking. It is called overhauling, and this is you. Sometimes it is useful. If you see an Yankee screwdriver, you must have seen it. That some, if the worker or the person pushes it, the head will, it will keep rotating. Okay, so basically it looks like something like this. You must have seen it. If you push it from the behind, it will, the front side will rotate, and you can apply the torque. So this concept is used like, if you push it, you are putting the torque, and then to lower it, you will not require any torque. It will rotate by itself, right? This is the concept called as overhauling of the screw. But this is useful a few times, but most of the times it is not useful. That means your screw should not come down by itself, because, like, say, take an example of a screw jack. If you are pulling up a vehicle with the help of a screw jack, using square threads, and if you take out the input torque, then it will come down by itself. Then it will be a hazardous, or it will be accident. It will make, cause accident. So to avoid that, we have to make sure that your screw will not come down, or lowering the load. The torque required should always be positive. Okay, that is very important property required for a screw, that it should not come down without putting the torque, you know and for that, empty has to be positive, this empty. And that means what? To have this positive, your phi should be greater than alpha. What is phi and what is alpha? We have seen that. What is phi and what is alpha? Here phi is, or alpha is, we have seen helix angle, and phi is equal to your angle of friction. Mu is equal to coefficient of friction is equal to tan phi, right? So if your, when phi is equal greater than alpha, that means your positive torque is required. This empty will be positive. Again, I will repeat. When in this is the torque required to lower the load, right? In this equation, when phi is greater than alpha, that time the torque will be required to lower the load. That means your screw will not come down by itself, and this property is called as self-locking. Means it will not come down, or it will not lower without giving the effort, and which is an important required property. And these properties, this kind of screws are called self. They will not come down by itself. They are called self-locking screw. Means for this screw, what is the property? Phi is greater than alpha. Alpha is helix angle, phi is the angle of coefficient, angle of friction. Okay, so angle of friction should be greater than alpha. Means what is angle of friction? It is basically related to the friction. So your friction should be more. If your friction is less than beyond certain limit, then your coefficient of friction will be, this phi will be less, and your, if your helix angle becomes more than that, then this equation becomes negative, and the screw will be overhauling of the screw. It will be overhauling screw. It will not be a self-locking screw. So what is the self-locking property? Self-locking property is a property by which a screw will not come down by itself, but it will need a torque to lower itself. And for that, the important condition is that phi is greater than alpha. Okay. So we have seen now that phi is greater than alpha for self-locking screw. That means what? What is phi? Tan phi is your coefficient of friction, and alpha is your helix angle. So if we put tan on both sides, you will get tan phi is equal to mu, coefficient of friction, and tan alpha. We have seen that. What is tan alpha? Tan alpha L upon pi dm. We have seen that triangle. Let me show that again. Okay. So if you see this triangle here, tan alpha is equal to L upon pi dm. L is lead, pi dm is your mean diameter circumference. Okay. Okay. Let's go back to the equation. So mu, coefficient of friction, should be greater than L upon pi dm. This is the equation required for a self-locking screw. Is it clear? Okay, now again I will repeat quickly. We'll go through. A self-locking screw is a screw which will not it will not come down by itself. It will need some effort or torque to lower. And for that, the condition we will use the equation for lowering the load. And to make that torque positive, always phi should be greater than alpha. So for self-locking screw, the equation is phi is greater than alpha. Tan phi, if you take about tan of both sides, you will get coefficient of friction should be L upon pi dm. That means it has to have certain friction. If the friction is very less by by self lubrication or something like that, if we put too much lubrication in like a screw jacket, if the friction come down drastically, then it will not be self locking screw and it will not serve the purpose. Okay. A screw is self-locking if the coefficient of friction is equal or greater than the tangent of the helix angle. This is the what you can say sentence for the self-locking screw. What is that? For self-locking screw, your coefficient of friction is greater than your tangent of the helix angle. Okay. Yes sir. कुछ काम था क्या? बोलो ना.
सर मैं आपसे तो हार्ड कॉपी लिए.
Okay, sorry guys, somebody came to visit me. Okay, so basically we were saying that for a self-locking screw, your coefficient of friction is greater than tan of helix angle. Now, some important what you can say conclusion that a self-locking screw is means that is what when coefficient friction is very low means if we put too much lubrication, self-locking is not possible because coefficient of friction has to be greater than tan of alpha. So if we have a screw and we know tan of alpha, we know the helix angle and we know tan of alpha, and if your coefficient of friction is very low, then your self-locking will not have happen, and that is the case when we do excessive lubrication. If we put too much lubrication, we will basically um, uh, we will make a issue with the self-locking screw. We will make it overhauling of the screw. Okay. And again, one more thing. This is also tan alpha is coefficient of friction is what is tan alpha? Pi dm. If your lead is too big, then this right hand side becomes big and this equation will not true. That means what? If your lead is, if it is a multi-star thread, two star or three star, your lead will be for two star thread, L will be 2 of pitch, or for three star L will be 3 of pitch. So if L is large, like a multi starting threads, that time your scale blocking screw will equation will not remain valid because your this right hand side will become larger and your left hand side becomes smaller, right? So for multi we generally we do not use multi-started threads like double or triple started threads for self-locking screws or like example like Screws-Lect. Are you getting it? So there are two things we need to remember. First, if the friction, if the lubrication is too much or if the friction is very low, that time self-locking screw will not work because right hand side will become very less, right? This equation will not remain valid. And second, if L is large, that is lead is large for multi-starting threads, that time also this equation will not remain valid and we will have issues with the self-locking screw. Okay, so this is the concept of self-locking screw, and these screws are used like important applications like the screw jack, where we do not want the screw to come down by itself. There the torque must be given to lower the load. Okay, so that was the concept of the self-locking screw. It will lock itself. It will not come down without putting input, giving torque. Okay. Any doubt, any queries you guys have? Let me just quickly take this as a chance to take my attendance. Okay. Okay. So attendance is there. I saved it. Now let's go back to the our lecture. Now let's get this second concept. Now, what is collar friction? This is important. Okay. Hopefully, there is no doubt. I haven't seen any queries, so I hope there is no doubt or queries from you guys. Nothing in the chat. Okay. So I hope the concept of uh, self-locking screw is clear. Okay, we will use that in some problem. Now we will see what is the collar friction. This is the important concept which we will use in for the design, because we have seen now what is the torque required to raise or lower the rod, right? We have seen that. What is that? It is W into dm by 2 into tan phi plus alpha to raise and tan phi minus alpha to lower. Now this is one torque. There is one more torque, because sometimes what we do, there is always, obviously, your screw is rotating, right? So you cannot attach this screw to your what you can say part or the item or the object which we are trying to raise or lower, right? Whatever it is, it may be clamp or anything, it may be C clamp, whatever it is, we will not try to put a rotating component in closeness, or there will not be any contact between the object and the screw. So we will use something called as collar in between. The collar will be fixed on the object, whether it is lowering or clamping or whatever is the function. But we will have a collar in front of the screw, and there will be a motion of or the friction between the collar and the screw. So the object is not, what you can say, it is not having any kind of friction or wear. Okay. Now, since we have something called as this collar, right? See, I have shown that in the diagram. There is a collar. Like if you see the something as a cup size, there is a collar and there is a cup. So this cup will be attached to the object or will be in contact with the object, and there will be friction between cup and this collar. Okay, the collar is what at the end of your screw you will have enlarged diameter. That is something called as collar. It is what you can say extension of the screw. Now, when your cup is fixed, it is not rotating, but your collar is rotating. Okay, in this, if you see the diagram, there is a cross section that is cup, and there is a collar. Okay, so there will be a friction between collar and cup, and because of that you will need extra effort to overcome this friction so that the screw rotates against a fixed cup. Are you getting my point? I will repeat again. When we want to put this square threads into application, the threads will be rotating, right? But we do not want these to come in contact with the object, so we'll have something called as cup, and which the cup will come in contact with the object, and there will be a motion between a part of the screw collar and cup, a frictional motion, and to raise or lower or to rotate the screw, we have to overcome this particular friction, and the torque required to overcome this friction is called as collar friction torque. Are you getting my point? It is very easy concept, and it's very easy to calculate that this collar friction torque, but we need to understand why we need it. There are two. First thing is we will need a torque or the effort to raise or lower or clamp a load. That is what we have seen, that mt is equal to w into dm by 2 tan phi plus or phi minus alpha, depending on the application. But apart from that, since we cannot put our screw in contact with the object, we have to put some another component called as cup, something like that in between, and there will be a friction between collar of the screw and your particular this cup, and this effort or torque required to overcome this friction is called as collar friction torque. Clear? So this is the concept of basically collar friction torque. Now we need to calculate what is this torque. Very simple. Now see where is the friction is happening between. There are two diameter of the cup has a hole in it, right? It has the diameter DI and DO. So between these two diameters of the collar, or say see DI is equal to basically your root diameter of the screw, right? DO is the outside diameter of the collar, right? So between these two, if you consider, see the diagram B, there are two circles are there. The one is inside is the DI, outside is DO. So DI is the from where the friction starts, and DO is till where the friction happens. So basically, the friction will happen in this area. Now, what is this area? Pi by 4 di square minus do square minus di square. Very simple. This is the area of the friction, right? So between this area, the friction will happen, and we have to overcome this friction to to raise or lower or 2 over the collar friction. Okay. So now how to calculate it? There are two concepts. One is called uniform pressure theory. Actually, we have seen that in strength of material. Uniform pressure theory. The torque for the collar friction is mu c into W by 3 dO q minus diq upon dO square minus di square. This is the uniform pressure theory. And wear theory tells us the torque required for collar friction. This is mu c into W upon 4 into dO plus di by 4. This is the concept, or this is the using wear theory. Now here coefficient of friction is mu c, dO is outside diameter, di is inside diameter, and mtc is collar friction torque. Now this uniform pressure theory is used in a for new threads, or when the collar is new, means it is not having any kind of wear and tear. But once it starts wearing, then we will use uniform wear theory, right? So generally, I know, we use uniform wear theory for the practical purposes, right? So how it is mu c into dm. So what is now what is the uniform wear theory tells us what is the collar friction torque? It is mu c into w upon 4 into do by do plus di. Okay. Now if you see di plus do by 2 is what we have seen that in here. Okay, while looking at the concept, we have seen here dm is dO plus di by 2, right? Or it is outside diameter plus inside diameter by 2. This is for the square threads, but same concept is we can apply here. If you see the collar, what is the di plus do is mean diameter of the collar. Now similarly, like it is not that the collar diameter, outside diameter may be more, it will be more, but to find out the mean diameter is d inside diameter of the collar, outside diameter of the collar by 2 will be your mean diameter dm. So if we take that, then we will get this equation as mu c into w dm by 2. This di plus do by 4 will be dm by 2, and this is the equation of the collar friction. Okay, mu c into w, okay, is equal mu c into w into dm by 2, where dm is equal to mean diameter of the collar, di is inside diameter, do is outside diameter, right? So collar friction torque, or the torque required as per the uniform wear theory, torque required to overcome the collar friction is mu c into mu c into w into dm by 2. Okay, so now we know what is the torque required for collar, what is the torque required to raise or lower the load. Now we can use these torques and we can add them to find out or to calculate the total torque. Now we will use this total torque to for the design of the different screws. Okay, okay. So now to recap, what we see to what we have seen today is, first we have seen what is self-locking concept. That is, self concept is when phi is should must be greater than alpha. What if phi is your angle of friction and alpha is angle of helix? So coefficient of friction should always be greater than tan of alpha, tan of helix angle, to make your screw self-locking. That is the one important concept we have seen. Now, so for self-locking screw, right, coefficient of friction should not be very less, so lubrication should not be too much, and L should be high. The screw should not be multi-starting. And then we have seen different types of, or we have seen collar friction torque, that is MTC. We have come to the conclusion that coefficient torque required for collar friction is mu c w into dm by 2, where dm is mean collar diameter. Okay, and we will add this to this equation, that is equation to raise or lower the load. That is, where is that? Okay, this w mt torque required to raise the load is w into dm by 2 into 10 phi plus alpha. We'll use these two combination to find out the total torque to raise or lower the load. Okay, so these are the concepts for today's lecture. So I will wrap today's lecture here, and in next lecture we will see what are the stresses in power screws, and now how to design. Basically, design means what? We have to design the screws, what type of threads we will use, what is the lead pitch, minimum diameter, outside diameter, inside diameter, all that, all those things we will see in next lecture. Okay, so hopefully the concepts are clear. If you have any doubt, you can ask me in the chat. Okay, hopefully we have 11 participants. Hopefully there is no doubt. If it is there, you can ask me in the chat. Otherwise, we'll wrap up today's lecture. Okay. Thank you, guys.